Okay, girls. So, ladies, today we're going to talk about the connection between work, force, distance, and energy, right? Now, we've been talking about force, and, you've been able to analyze, like, Newton's three laws and be able to do calculations involving friction and net force. And so today we're going to extend and we're going to talk about the role of force in something called work, okay? And work, we have two definitions of work. Actually, so we have one definition of work, but we have different ways we're going to calculate work, okay? So the definition of work that most people often use is this one here. Work is defined as a change in energy, okay? And it's so if we define it as a change in energy, you'll have an equation right over here, which would summarize this. And that's this equation, right? Work is the change in energy. Now, what we'll talk about later on is really that tells you something about energy and work, because they're actually the same thing. Energy and work are really just two sides of the same coin, because you can really just say a change in energy is the same as work. So if I said to you, give me an example of work, right? Well, okay. Would lifting a barbell be an example of work? So then if we do work on the barbell, you're changing the energy of the barbell, right? Why? Because you're lifting it up. And you know that if you let it go, it's going to fall and it's going to hit the ground with a lot of energy, right? But think about the reverse of that. For you to lift a barbell, that had to be a change in energy, right? You have had to convert your chemical energy into mechanical energy to lift that barbell. So work and energy are actually the same thing. They're just two sides of the same coin. And later on in this course, you'll realize that electricity and magnetism are actually the exact same concept. They're also two sides of the same coin. So we're going to talk about work today, but I do want to point out something about work that you need to understand. It's very, very fundamental. Work is going to be, we're going to define it as a product of, well, we're going to start with one equation of work, which is force times distance. But you need to understand that those two components have to be parallel to each other. Okay? So we're going to start with this equation over here. Work is force times displacement to define or figure out what work is, but they have to be parallel. So if you look at this picture of the Earth and the Moon, right? So why does the Moon orbit the Earth? Because of gravity, right? If you were to visualize the motion of the Moon around the Earth, what is it? It's circular, right? And if you were to figure out at any point where is its velocity vector, it's always pointing, and I think we may have talked about this. Yeah, I don't know. There's nothing there, though. The velocity vector is always pointing perpendicular to its motion. But think about the work or the force of gravity. It's always pointing towards the Earth, right? Or you can think of it the other way, too, that the Moon is pulling on the Earth. But if you look at those two vectors, you'll notice that they're not parallel. They're perpendicular. So first thing you have to understand, when we go ahead and do these calculations, you need to identify the force that's parallel to the displacement. Not the force that's perpendicular, it's the force that's parallel. Keep that in the back of your mind as we do these calculations, all right? So if we're going to define work done by a particular force, it has to be the force that's parallel to the displacement that we're analyzing. So let's take a look at, so right in this case, there would be no work done by gravity. Yeah, none, because they're perpendicular. Well, there is, there's no change in energy relative to that force, right? So let's take a look at some examples with this equation where work is defined as force times distance. Again, remember, force and displacement have to be parallel. Okay? So look at one really simple question here. We have 100 kilogram mass sliding over a surface. We have the coefficient of friction and we have the displacement. Okay, and sliding over with a, we're going to slide it with a constant speed. Okay, we're going to slide it with a constant speed. Now, we're going to start with the equation for work, right? We're actually going to derive another equation. So work is force times distance, right? And those two have to be parallel. And if they're not parallel, then we have to figure out what we can do with the force. We might have to break it down into the vector components and find the parallel component. Okay, unless it's perfectly perpendicular, then the answer is there's no work. Now, we also know that force is mass times acceleration, correct? So we can derive another equation where work, and I always suspected this, work is mad. Right? Work is crazy. Now, the unit of work is the joule, but let's see what the joule looks like. So if you think about, we know what the unit for mass is, right? Kilogram. What's the unit for acceleration? Meters per second squared. And the unit for distance will be also in meters. This gives you kilogram meter squared per second squared, or you can think of it as kilogram meter per second squared. So in other words, mass times speed squared is the unit of energy, and that is the equivalent of what's called a joule, okay, which is written as a J. So if we went with this equation, force times distance, what's the unit for a force? Newtons. So this would be a Newton meter, right? So a Newton meter is the same as a joule, which is the same as a kilogram times speed squared. And that's why we can think of it also in terms of the energy of, one of you mentioned before, examples of energy, like kinetic energy is one, which is the energy of motion. But we'll talk about that one later on. Okay, so let's look at this question, all right? So we have the mass of the object, which is 100 kilograms. Now, so we have mass. Let's write down what we have. We have displacement. What we don't have is acceleration. Okay? That's what we don't have. But we have a clue in this question. Told that the velocity is what? So you might be arguing, okay, wait, if the velocity is constant, then there is no what? Acceleration. So then isn't the answer 0? Because if we plug in and we use MAD equation, then A would be 0. But then that doesn't make sense because you are pushing it, so you have to be applying a force, right? So now we got to think of this question a little bit differently. So maybe we should draw a box. So here's my box. Here's the ground, and it's moving this way. Okay? Now, we're applying a force, but if it's sliding at a constant speed, then that means that this force has to be the same as this force. That's why there's no acceleration. It's not because there's no force. It's because the two forces are what? They're equal. They're balanced. Now, can we work out the force of friction? Why? Because you're given what? You're going to give the coefficient, right? So, in this case, we're going to assume that we are not pushing up or down on the box. So, in other words, we're going to assume that the weight is equal to the normal force. Now, that's the situation if the thing is sliding perfectly horizontal and there's no pushing and pulling vertically, then we can say the normal force is the same as the weight. How would you figure out then the force of friction in this case? So yeah, it would be what? The force of friction is the same as mu times the normal force, right? The force of friction is the same as then mu times the weight, because the normal force is the same as the weight. So in this case, the force of friction would be mu, which is 0.1, times the mass, which is 100, times g, which is 9.8. So I believe it's 98 newtons, right? I believe the answer is 98 newtons. Okay, so now we have force. So I'm going to write down up here. Yep. Yeah, because the weight is the same as the normal force. Yeah, Fg equals Fn. So friction is mu Fn. Okay, now you have two ways you can calculate work. One is you can just do force times distance. The other one is you can do mass times acceleration times distance, right? So maybe in this case it's actually easier to use the force times the distance because we already worked out the force, but then I'll show you how we can do it with acceleration. Exactly. So if we think about the work that you're doing, it's the force that you're applying times the distance, correct? Now, in that case, we worked out the force of friction is 98, and that's pointing left. Your force applied is pointing right. So it would be 98 newtons to the right times 20 meters. That works out to what, 1,960? And that would be joules. Now, here's the thing. If I said to you, what's the work done by friction? Well, that should be the same. The work done by friction then would be the same answer, but it would be 1900 joules to the, in this case. Now, here's the thing about energy, right? Energy is a scalar quantity. So, but we can still talk about the direction of the force. So in this case, the work done by friction would be the opposite way. It's still 1960 joules of energy. So that's one way to calculate work. If you wanted to do it with just the acceleration and not the mass, then, in other words, if we want to use this equation, MAD, and not work out the force, how could we have done it? Think about mu for a second, right? What was mu defined as? Mu is what? Mu equals FF over Fn, right? Because you can rearrange that for force of friction. Now remember, in the situation, again, in only this situation where the normal force is equal to the weight, then we could say that the mass times the acceleration due to friction is the same as the mass times g. What do you notice in this case? That cancels out. You can then rearrange for the acceleration due to friction as a function of mu times g. But again, this is only when what? Fn equals Fg. Okay? So if you look for the acceleration due to friction, then we can use this equation now. Because now we have the mass of the box times the acceleration, mu g, times the distance. Now remember, if you think of it in terms of acceleration, remember this. If this box is moving at a constant rate, that means the net acceleration or the net force is what? 0. Friction is pointing to the left. Applied force is pointing to the right. There is an acceleration due to friction pointing to the left, but there's the same acceleration due to the applied force pointing to the right. So we can think of it in terms of accelerations too. So you know how Newton's second law says if there's a net force, and net force is 0, then there's no acceleration? You can think of it the other way around too. If the net acceleration is 0, that means the net force is 0. If the net acceleration is 0, that means the acceleration on one side is the same as the acceleration on the other side. So if you can work out the acceleration due to friction, you could use that acceleration to figure out the answer. And guess what the answer is going to be? It's going to be exactly the same. Okay? So there's more than one way to do these questions. Okay, let's look at the second question. All right? So remember, now this one here, you're gonna have to think about that whole concept of the force and the distance having to be parallel. All right? In the previous example, we didn't have to worry about that, but in this one we do. So in this scenario here, you have a person who's going to walk up a ramp. Okay, so I'm going to walk up a ramp, and a ramp is going to be 10 degrees, although it's more like 30. And the ramp is going to be 20 meters long. The angle will be 10 degrees. Okay? And we want to know how much work is done against gravity. So that's a clue. Against gravity means what? Which way? Vertically. So if we're talking about an applied force vertically, then we need to think of which component of this ramp. Yeah, we need to think about this component. So when we go ahead and calculate work as a function of force times distance, we can't use any distance. Because if we're talking about the work against gravity, and that's pointing up, then we need that parallel component, which is, in this case, the vertical component of this ramp. So we can say, okay, well, work is force times distance. So force times distance. Now, distance will be what? The opposite side. So that would be sine 10 times 20. Okay, so that's our vertical component, right? So not 20. Now, here's the question. If I change this to, because when you walk up a ramp, it's not like you're sliding your sorry butt up that ramp, right? You're walking. But imagine that you were like a box and you were sliding it up the ramp. Okay? Now, keyword, you're sliding it up the ramp, which means there's a lot of contact between the box and the ramp. Now, we have to think about, well, there's also friction, right? So now we have to think about, well, the work done in that scenario is going to be a little bit different. Because now we can think about work being done parallel to the length of the ramp. But we'll deal with that scenario at a different time. Okay? So right now we're going to assume no friction. So the force up, we have the distance up. Now the question is, what's the force up though? That's a good one. What's the force up? Well, you're going up a ramp. You're going against gravity. It would be applied, but what would it be equal to though? So we're going to have to make an assumption here, okay? We're going to have to make the assumption that the net force acting vertically is 0. That means that you're moving up the ramp at a constant rate. Otherwise, you can't answer this question. Okay? So if we're moving up a ramp at a constant rate, that means that there is a force acting up, but there's also a force acting down, and those two have to be what? Right. So what would the force, so here's my person, I'll go over here. What's the force acting down? What's the force acting up? Call it the applied force. Those two have to be what? So then we know what that force is. The force would be the same as the weight, but just pointing in the opposite direction. Okay, so what is that? So what's the weight? Weight is mass times g times sine 10 times 20. So it's 50 times 9.8 times sine 10 times 20. So what is the work done to move up the ramp? And it should be at a constant rate. So what does that end up being? 1,715 joules. Okay. Now, here's the thing. If it's not at a constant rate, I think Anissa was asking me about that. If it's not at a constant rate, then would the applied force be the same as Fg? So then you have a problem, right? Because then you won't know what that applied force is. Okay? That's a good question. So ramps is something that we don't really deal with in grade 11. We could. It would actually. So we'll talk more about that in grade 12. But the normal force number has to be pointing perpendicular to the surface. So it would actually be this component right here. Okay? Well, unless we include friction, well, actually there has to be friction, otherwise the person will be declined, but we're ignoring the effects of friction. You'll see that when we talk about ramps and situations with friction involved and the role of the normal force. And you can actually, you know what, I'll save that discussion for grade 12, because it can get pretty complicated. Okay. Alright, one last question, alright? With work. And we're going to look at this question right here, which is how much work is done by a hockey net if a hockey puck of mass 0.1 kilogram hits it with a speed of 90 kilometers per hour and comes to a stop in 0.050 seconds. Yeah, so it hits the back of the net and that moves back a little bit to stop the puck. Yep. Well, let's start with what we know. What's your equation for work? Work is force times distance, or we could use W equals mad, right? Okay. Now, we have, let's write down what we have. We have the mass, so that's given, 0.1 kilogram. We have the initial speed, which is 90 kilometers per hour. But remember, this has to be in what? Meters per second, right? So that's going to be 25 meters per second. I had that one memorized, so don't be impressed with my math skills. And then we have VF, which is 0, right? And now we have time, which is 0.050 seconds. Okay, so here's the thing. We can easily figure out work with our kinematics stuff that we've learned before, right? Because we have the mass, which is 0.1. Now, how do you get the acceleration? Well, okay, well that would be simply VF minus VI over T, right? So that would be VF minus VI over T. That's your acceleration. How do you get your distance? Well, that would be V average times T, right? So that would be V average times T. Remember that, right, from Unit 1? So how much work is done? You have the mass. What's your acceleration? So it's 0 minus 21 over 0.05 times the average of 25 and 0 over 2 times the time, which is 0.05, actually it's 0.050. Okay, so there you go. We can use our unit 1 stuff, our kinematics equations, to solve this. So, I know a lot of you were relieved when we finished unit 1, but you can see that we're not really done unit 1. So, what's the answer then? 625 joules? Oops. Wait, if you wanted to tell me which way the force was pointing, it would have to be opposite way the puck is moving. Yeah. But for energy, you don't have to describe the direction because it's not a vector quantity. Okay. All right. Yeah. That's it. I'm going to end there, but I'm going to tell you, I'm going to give you a task, and it's going to be on your next test. Okay? Whenever that test is. So I'm going to stop there. Okay, ladies? No, it won't be this week. Okay, the end.